So, welcome everybody to my talk about systematic use case modeling and specification analysis of transportation systems in the era of software-defined vehicles. And having seen the program of this conference and the program today so far, I have changed my talk because there were so many talks already about ODD coverage, ODD definition, end-to-end AI and AI and sensors and so on. So I now give a talk about the topic of software-defined vehicle, what we have also heard in the talk this afternoon, that like the ODD definition, it does not end at the SOP, but also the ODD definition goes further after the SOP. And this now applies to, in the era of software-defined vehicles, to all functionality in the vehicle. And in the development of a vehicle and of transportation and autonomous driving, from an OEM perspective, you have your driving stack and you have your systems that create all the capabilities of the driving stack, but you increasingly you also have interaction with other functionalities in the vehicle. So on the one hand, you can say, okay, I have my driving stack, and this is, let's say, a more isolated system. But on the other side, it's also beneficial to see how you have interaction of the driving task with other systems in the vehicle. For example, with what is starting from level 3 systems, that you allow other tasks in the vehicle, like comfort tasks, or also previous when you have like level 2 automation, that you think of maybe you use your energy management and all the stuff also in the context and interaction with your driving task. And in fact, now it does not stop at the SOP. Your ODD definition evolves further, your driving stack evolves, and also your vehicle evolves. And this is also what we have heard this morning, that the software-defined vehicle that captures, of course, driving automation, and there you must have something like a software-defined vehicle because you must be able to update your functionality. This now captures all functionality in the vehicle. And your hardware component and hardware component development is traditionally slow, and it will still be slower than the software development because of the development cycles of hardware and production, how you can update and introduce it into the production of the vehicle and so on. But your software, in contrast, you can update at a much higher frequency. You can more rapidly deploy new features in the vehicle to continuously increase the performance of the vehicle, to fix or to maybe prevent security topics, and to do maintenance updates during the whole life cycle of the vehicle. And this is a tremendous change. And now for this talk, after we have heard a lot about ODD definition and so on, I take now one step that comes after this, I would say, in the development cycle. That is the use case specification or the specification of the functionality, the capabilities that are then realized in the vehicle and which interact with each other, which interact maybe with the driving stack and which also interact with many other systems in the vehicle. And to ensure the completeness and the coverage of all relevant use cases when you do an update of the software in the vehicle is very important, because after the SOP you have then many more SOPs of the functionality in the vehicle, and at every SOP all the functionality must be consistently covered and validated before release. You can apply traditional methods like expert knowledge, so have all system engineers and all use case responsibles and all feature responsibles exchanged and talked about the realization of the features and the capabilities. You can do Monte Carlo simulation, but what is often missing is approach which guides you more towards that you can do this in faster cycles and in a common manner of all people working on the functionalities of a vehicle. So in this talk I would like to present a new method, structured modeling method for use cases of transportation systems, which you can apply on specific features of like your driving functionality and all the other systems that interact in the vehicle. Here's one example now of use cases for the energy management, use case specification, and also stakeholders of these different use cases. For example, the driver, the manufacturer, service technician like maintenance later on. And then you have the driving assistance systems. You have, of course, charging of the vehicle, energy management, and so on. And many engineers now create specifications and diagrams of all these systems. And the question is how you can ensure or how you can ease it that you, when many engineers work on all the systems in the vehicle, you can just put all these diagrams, maybe UML diagrams or whatsoever, then when you put all this together, that all this matches together. So that all interfaces, when you put this together, match and have a counterpart that fits on the same level of abstraction of the modeling and so on. And the first step is that you have a common understanding of the boundary of the system under consideration. So this is why I've said that this comes like one step after the ODD. So now we are really in the vehicle, and you must decide what are the boundaries of your systems, of your use cases, how they interact, and where you define this boundary. It's common that you might also work with different views, logical views in systems engineering. And one word about this from experience, it's important that when you define, when you exchange the use cases of the features in the vehicle, and you have logical views on the system, on the vehicle that you have in mind, then you map it to the physical system, that still this identical boundaries are preserved. So when different disciplines, from different disciplines, the logical views which were discussed and exchanged between the engineers and then are mapped to a specific architecture, that still this mapping is preserved. And on this page, a very simple drawing that you can decide, sorry, you don't see my cursor, that you could decide here now where to make this boundaries of all these views, of these logical views in the systems, where you then put together the functionality in the vehicle. So for example, for the energy management system in the vehicle, where you have an energy exchange of electrical thermal energy. You have different participants and you have different use cases on it, and you need this to achieve the capabilities for driving. You have to align where are your logical views, where are your system boundaries, which you draw for modeling. The next step is that you identify all the relevant input and output interfaces going across this different logical views on your system architecture, on the interacting systems, and to keep this also consistent. So here again an example for a part of the systems you have seen on the slide before for the thermal management system, that you define these interfaces on the same layer of your system modeling. This is important, which interfaces on this layer define the boundary of your system and where the information is exchanged between the different features in your vehicle, and where you also work on in further iteration and update cycles in the development of your features in the vehicle. So what comes next is that you start to identify the possible data exchanges on these interfaces. So of course, at this step, it's very important to, you have logical views on your system, that you also have a view on your data that is exchanged, that makes some abstraction or defines classes on how your systems interact with each other in different scenarios, because you don't want to go through every possible bit combination, like it was also the question before, how deep your ODD definition should go. So when is it over-engineered, and what is a good level or good level of detail, like for your ODD definition. The same holds for this task and for the step before. So what is a good level of detail on this layer so that you can perform these steps. And in this step, you start with the empty input, so there's nothing exchanged, and then you iterate over the different classes, equivalence classes that can be that represent the data, in the sense which functional behavior, which functional expectation you have from your partnering system in the vehicle. And this is a very important step when you do later an update in the of your functionality in the vehicle, because when you have done this for the functionalities in the vehicle and you update or you develop further specific functionalities in the vehicle and some not, you can use this to check whether the invoked functionalities on either side still matches and is still what you have had in mind when you have specified the features and you do your update, then that this is still maintained. You can check this afterwards by this. Modeling elements that you can then use after you have done this sequence. Of course, you identify logical states that describe how your interaction can be mapped to and how your different exchange between the functions can be mapped to. And you can use this also when you have, for example, field data that you derive probabilities that functionality transitions between one logical state of use to another logical state, or simply when you can map it to specific user inputs and outputs, you can map it to this model and see how often this is actually happening in the field and in the use of the vehicle. Exemplary functions for this, on the left a sketch for energy management, on the right a serial drawing for from series development, a drawing for a safety function, active safety functionality, in which you can also see that you find macro states and so logical macro states in which you can put in other states, subgroup them, what's actually happening and what your functionality should do. On the left, a sketch coming from the very upper left side in the vehicle, in the V model, in which system engineers do their first, put their first thoughts on the paper to define what could be logical transitions, and then you can see what are your possible exchanges between the systems that interact in the vehicle. So, the era of software-defined vehicles. What is now, to stress it again, is important that you have after the SOP many SOPs, and for every SOP you must be sure that also your specification, your use case description, your capability specification is still consistent for every update cycle. So it's very important that you have a method to keep all these artifacts in the development process consistent. This is a method to do this. It's a structured manner. So when you have, like for the vehicle architecture, you have different logical layers in systems engineering, and this method then allows you to think of how in these logical layers you work, that from all different disciplines and domains in the vehicle, this fits together. You can determine coverage on the basis of these models. And you can also, by applying this method, already find during the specification, if you find some inconsistency, especially after an update, after you have updated your system modeling, you can find out if there's an inconsistency to another model of your systems in the vehicle and desired functionality behavior. So, thank you very much for your attention.